Okay, let's get started. We began to introduce some concepts of structure and bonding last time on Tuesday. So just to remind you, we talked about atoms and atomic structure, which is made up of protons, neutrons, and electrons. We talked about orbitals, in particular S and P orbitals. So obviously electrons are discretely placed within atoms in the atomic structure in various orbitals. But what is this picture I'm showing you? What does that picture say? What is it? Do you have a hard sphere around every atom? Nucleus? No, it's just
cloud.
Yeah, this is not even a cloud of electrons. It's just the space where the probability of finding the one or two electrons in that orbital would be most likely. It's just a mathematical construct. We give it a visualization in a shape because that's how it makes sense to us. But keep in mind, that's not like a solid sphere. It's a probability of where you might find the electrons. P orbitals, so when we talk about the atoms involved in organic chemistry, carbon, oxygen, nitrogen, hydrogen, the main ones, but carbon, oxygen, nitrogen, we're typically talking about the second subshell, which has s orbitals and p orbitals in those atoms, right? One s orbital, three p orbitals, it can hold a total of 8 electrons, 2 in each orbital. And we want to fill that valence shell to be stable. In order to fill valence shells, sometimes atoms, particularly if they are far apart on the periodic table and can easily gain or lose 1 or 2 electrons, will ionize, they'll oxidize or reduce, and form mostly ionic compounds where we just have electrostatic attraction. And then we talked about covalent bonds. So covalent bonding is probably the most prevalent in organic chemistry because it's not easy to give up or gain completely the number of electrons it would take to get a stable valence shell. For example, carbon. Carbon needs to gain or lose 4 electrons to become stable, and then you can't easily get a 4 plus or a 4 minus carbon atom. So instead, it shares electrons. That's what we call covalent bonds. Right? In this case, it's sharing electrons with fluorines. And we represent that usually by lines, where we use a line to indicate the bond that's of the shared electrons in a covalent bond. Okay. And I talked a little bit about how we represent structures. So does anybody have any questions about skeletal line structures? So we'll use them a lot in this class. And I want to make sure that what we're representing is understandable to you. So any questions on skeletal structures?
Middle vow with carbon unless otherwise noted, right?
That's right. The element, atom is always carbon unless otherwise noted. So in this case, the structure I have there, keep in mind every end and every connection is a carbon atom. So this has, what, 5, 6 carbons in total. We draw all other atoms out, like this bond to chlorine here, except the hydrogens. So the hydrogens are assumed. You know that the number of hydrogens has to be enough on each carbon to make up a total of 4 bonds. Right? It's carbon bonds to 4 things. So it needs 4 bonds to get its stable octet around it. So for example, this carbon on the end, right? If I draw that carbon out, it's bonded to another carbon. That would be this carbon, right? How many hydrogens have to be on this carbon here? 3, right, because it only has 1 other bond. What's not written are 3 hydrogens. I could draw it condensed, or I could draw them out, and so on. So if anybody has difficulty understanding skeletal structures, please let me know, and we can clear that up. Okay, we're just starting to talk about other kinds of bonding and structure in organic molecules besides the typical S and P orbitals. So I left you with this observation that the molecule methane, okay, CH4, is a completely symmetric structure in 3 dimensions. It forms a tetrahedron the atoms of hydrogen around the carbon are spread out equally. Okay, so between each hydrogen carbon bond, it's 109.5 degrees. If you were to measure that angle on any one of those, this one would be also 109.5 degrees. Okay. And if you think about this, remember these bonds between carbon and hydrogen are a shared covalent bond, right? So the electrons have to be in that bond. And if you think about how those atoms might share those electrons, what has to happen is the orbital on carbon that contains that electron and the orbital on hydrogen that contains that electron have to overlap with each other. Okay? So if we have a structure of carbon, if you think about the atomic structure where you have an s orbital with 2 electrons on it, right? 2s2, 2p2. That would be the valence shell of carbon, right? The p orbitals we know are dumbbell shaped. If we look at the calculated shape of those, so you'd have a dumbbell shape in one direction, say the z direction, another one in the x direction, and another one in the y direction. So 3 p orbitals. And the electron configuration would put those electrons, let's say we have one electron in this orbital. That includes all of this, right? And then another electron in this orbital, and then this orbital is empty. If that's the atomic configuration of a carbon atom, how do you get the structure that we observe for methane? How do you get a tetrahedral? These angles here in this atomic carbon, what would be the angle between this orbital and this orbital? 90 degrees, right? That would be 90 degrees. If you have a hydrogen atom that comes along and wants to bond to this, let's say the hydrogen atom just has an s orbital, right? Let's just say we have a hydrogen atom here with 1 electron. It's got to overlap to form the bond, right? So if I put a hydrogen atom there, that would satisfy that orbital in that x direction. Okay, we could put a hydrogen atom here. That would overlap with the orbital in that direction. Okay. Then we have an empty orbital. We're not going to just put 1 electron there from a hydrogen, and we have this one that's already filled. You can't overlap in that orbital. How do you get the other hydrogens on there? And that's the thing that we need to consider when we look at the structures of molecules. Atomic structure represents what the atom would be in its neutral atomic state before any oxidation, reduction, or bonding. Okay? It's not the same structure of the atom when it's bonded in molecules, and that's important to recognize that anytime we form molecules, we want to become more stable, and the way that would be the lowest energy or most stable would be to take all the electrons in bonds, all the electrons in these covalent bonds here. Electrons repel each other, and they'll repel as far apart as possible, given the connection to that center atom, right? That's the maximum distance away from each other those bonds could be. This would be in the shape of a tetrahedral. That's why it forms that. It's the most stable spatial arrangement for those electrons. But the orbital configuration of the atom doesn't explain it, right? So we have to be able to explain this somehow. Well, in fact, what happens is that, again, these are mathematical probabilities, the shapes of orbitals. When we form molecules, these orbitals kind of mix together, and the mathematics explains this. But it achieves the most stable spatial arrangement by forming new orbitals, which we call hybrids, at different energies. Different energies than the atomic orbitals. So, if you think about and the way we try to explain this is to think about those orbitals mixing together and then coming out with brand new orbitals with different shapes and spatial arrangements. So in the atomic structure of carbon, we have an s orbital and 3 p orbitals, right? And if we fill those electrons from the lowest energy to the highest energy, they're spread out like this. That's our electron configuration. In the atom, take all these orbitals, throw away the shapes and what we have, mix all that mathematics together, and come out with a probability that would give 4 equal orbitals. And in this case, it looks like this: 4 orbitals, all the same energy. It has characteristics from both. We would call this a hybrid orbital. And the term sp3 here indicates that these orbitals were made up of originally the atomic 1s and 3p's. Okay, makes sense, right? The shape of those orbitals is more of a single lobe, although I've drawn on here a little bit of a lobe in the back because it reflects some of the p character. When we draw those actually on an atom, we tend to not draw that because it gets too difficult to draw. But if you take these 4 equal energy orbitals now, put an electron in each one, that's a new configuration for the carbon atom when it's in its bonded molecular state. Okay, and if you take each of those orbitals and splay them out as far as possible, you get a tetrahedron, and then those can bond with hydrogen. So you can see here the hybrid sp3 orbitals, and there are 4 of those, around the carbon atom. Now the hydrogen, s orbital from the hydrogen, can overlap and form the covalent bonds. That explains the structure that we observe for methane. Okay, so again, sp3 refers to a mixing of 1s and 3p's, so all of those atomic orbitals of carbon mixed together to form 4 equal orbitals, 4 equal sp3 orbitals. And you can see how that would work. Okay, now when these carbon atoms are hybridized in such a way, they can bond with other things besides hydrogen. They would bond with the fluorine. Also, the carbon would still be hybridized in an sp3 state. It can bond with other carbons. So when we mix these orbitals and form sp3 hybrids of those orbitals, in this case we have 2 carbon atoms, one here and one here. They're still tetrahedral in shape, but now what we have is a bond between the 2 carbons, where instead of taking an sp3 orbital and overlapping with an s of a hydrogen, we've taken an sp3 orbital from one carbon and overlapped it with the sp3 orbital of another carbon to form a bond between them. Okay, so that is a sp3-sp3 bond. When we have this sort of end-to-end overlap of orbitals, that type of bond we refer to as a sigma bond. That's why you see this little sigma. All of the bonds in ethane are sigma bonds. The CH bond is a sigma bond between an sp3 carbon orbital and a s orbital of the hydrogen. Okay. So in this molecule, in the ethane molecule, how many sigma bonds are present? In the whole molecule. How many sigma bonds in ethane? 7, that's right. There are 7 bonds, 7 single bonds. Those are end-to-end overlaps or sigma bonds. Those are typically some of the stronger types of bonds, sigma bonds. And there are 7 in this molecule. Question?
Just to be sure, you were saying single every time, right? Because I got the impression you were saying sigma, and I was really confused.
We call this a sigma bond. Yes, we call this a sigma bond.
Oh, okay.
When you have an end-to-end, a single bond is a sigma bond. Yes.
Okay.
Yeah. Okay. What about water? Have you thought about what the structure of water is? If you think about the atoms, H2O, and you were to just write them out thinking, well, we just want those atoms to be, as far apart as possible, you would draw something probably like a linear molecule, right? Like that. But in fact, the structure of water is not linear, it's bent. And it has an angle of about 105 degrees, as you see here. Okay, and how do you explain that? Why would that be the case? Again, if you were to think about this just from the atomic configuration of oxygen, how many valence electrons does oxygen have?
6.
6, that's right, and it wants 2 more. So again, if you think about the structures, here's the s orbital, and 3 p orbitals. This one would be filled, 1, 2, 3, 4, 5, 6, right? That might be the electron configuration. So if you were going to do bonding in this configuration with a hydrogen, here and here, again, what would the angle be between those? If these were p orbitals? It's 90 degrees. That would be, it's a right angle, right? Sorry, I'm drawing all over the place here. It's 90 degrees. That doesn't explain the structure of oxygen, of water. In fact, other atoms besides carbon hybridize because it's the most stable, lowest energy state. And that's because there are orbitals which are already filled with 2 electrons, lone pairs we call them, and I've drawn it here, the lone pairs on oxygen, which also have electron repulsion between each other, each lone pair, and the bonds. And so just like carbon, which happens to have 4 bonds to things, each of those covalent bonds has 2 electrons. This has 2 covalent bonds to the hydrogens, and then 2 lone pairs. Those electrons are still all repelling each other and want to be as far apart as possible. And the most stable form for that is a tetrahedron, if you consider the non-bonded pairs. A tetrahedron of the electrons. So again, what would you predict then the hybridization of oxygen to be? What kind of orbitals are they? sp3, right. All those orbitals, we still have to have 4 orbitals that are filled, and to be a tetrahedral structure, they have to be mixed with 1 s and 3 p's to make 4 equal kinds of orbitals. So in this case, what we have is an sp3 orbital here, an sp3 orbital here, an sp3 orbital here, and an sp3 orbital there. It just happens that those happen to overlap with the hydrogens. Okay, make sense? Many atoms do this, many other atoms do this. Nitrogen, for example, does the same thing. What's the number of valence electrons for a nitrogen? How many on nitrogen? 5. 5 valence electrons. Okay? It's between carbon and oxygen. Carbon, nitrogen, oxygen, right? So if you think about a molecule, if it's 5 valence electrons, it can form how many bonds? 3. It needs 3 more electrons, so it'll form 3 covalent bonds. So if you think about the molecule ammonia, NH3. Right? And the Lewis structure for NH3, there's a lone pair plus 3 hydrogens. So nitrogen also, guess what the shape is if you consider the lone pair as taking up space? Nitrogen is not a flat molecule. There's a lone pair, there's a hydrogen here, hydrogen coming out at you, and a hydrogen pointing to the back. It's really kind of a pyramidal shape, but if you think about the lone pair, not bonded to an atom, but it takes up space. So it has a similar kind of tetrahedral structure in the arrangement of the electrons in bonds and in non-bonding pairs, right? Guess what the hybridization is? sp3. Hybridization of nitrogen is sp3. It's all the same. Okay. So any questions on sp3 hybridization? What that looks like? Yes?
Why is the angle between the hydrogens and methane different from the angles between hydrogen and H2O?
Great question. Why is the angle in methane? All the angles are 109.5 degrees, and in H2O, that angle between the hydrogens is a little bit smaller. Well, it actually turns out that depending on whether something is bonded, those electrons are maybe further or closer to the atom, and then things also take up space. So if the molecule is not symmetric, if each of those four orbitals is not symmetric, you see a little bit of skewing of that. So it's not exactly 109 because there's no other, because these lone pairs, there's no other nucleus out here which pulls those electrons away and makes them less repel. So these are repelling a little bit more, which pushes those hydrogens a little bit closer. Now, if you take a look at, let me just go back a slide, 2 slides actually. If you take a look at, oh no, where is it? Well, I don't have the angles here for ethane. I think I have it on the next slide. Yes, okay. Here are the molecules methane, which we talked about, ethane with 2 carbons, and now propane, which has 3 carbons in a row. You see a similar thing. It's not exactly symmetric because each of the 4 bonds are not bonded to the same things. So, for example, methane has 4 equal bonds to the same atom. It's completely symmetric. All 109.5 degrees. All the bond lengths are exactly the same. In this case, 1.09 angstroms or 109 picometers. Take a look at ethane here. Notice that the bond angle from hydrogen to carbon, that bond angle is not 109, it's a little bit larger. Why do you think that's a little bit larger? Yeah, the carbon, yeah, actually, steric size. So if you think about this, we have a small hydrogen here, which is pushing against all of these other ones, right? Here we have these same 3 hydrogens, but then we have something that's much larger. That's going to push those further that way. Okay? And in the lowest energy, it would be a little bit further. So this angle here opens up between these hydrogens to that carbon. That bond angle becomes a little bit larger. Guess what happens to the bond angles between the hydrogens? And it's not listed here, is it? No. The bond angles between the hydrogens get a little bit smaller. So depending on the symmetry of the molecule and what size of groups are attached and how much electron repulsion, these bond angles will shift just a little bit to accommodate that. Okay? Any other questions? Same thing you see for propane here. Notice the angle here, carbon-carbon-carbon angle is a little bit bigger. And that pushes the other angles away also. So all these little tweaks do affect the structure in these subtle ways. Well, another type of bonding we can have in molecules, actually it's possible to form shared bonds, covalent bonds between atoms, more than one. So in this case, here are a couple of molecules, carbon dioxide, and hydrogen cyanide. This represents multiple bonds between atoms. So in the case of carbon dioxide, for example, we have the bonds between carbon and oxygen. In order for everything to get an octet, and be stable, you have to have 2 bonds. There are two bonds here and 2 bonds here. These are what we refer to as a double bond. Okay, double bond. We can have a double bond between many kinds of atoms. We have lots of double bonds between carbons, carbon to carbon. We can have double bonds between carbon and oxygen, carbon and nitrogen, etc. And sometimes we even see 3 bonds. What we refer to as a triple bond, which is the case here in hydrogen cyanide. Okay, so now we have to think about again, when we have this kind of bonding between atoms, how do we describe the orbitals that explain the shape of the molecule? And I'll tell you, both of these molecules happen to be linear molecules. And maybe I can come back to that. Well, let's take a look at a double bond. Here's organic examples: carbon-carbon double bond and a carbon-carbon triple bond in these simple organic molecules, ethene and ethine. Okay, and the shape here, what we see is that this ethylene molecule is, if you look at the hydrogens and carbons, and you look at it from the side, they all lie on one plane. It's a flat planar molecule. Oops, sorry. It's a flat planar molecule. And although the carbon and hydrogen is a little bit different, roughly about 120 degrees. This one will be a little bit larger. This one will be a little bit smaller. I'll just say 120 degrees. Okay? That would be in one plane, the furthest apart they could be 120 degrees. The acetylene molecule, or ethine, is a linear molecule. And this bond angle here and here are 180 degrees. Okay, how do we explain the bonding? How are the electrons on the two atoms that are multiply bonded overlapping? Okay, they're not all in that same space. Okay, they have to be originally made up from the original S's and P orbitals from the atom originally. Right, so let's think about that. Let's think about the double bond for a minute. When we have a double bond between atoms, the way to explain that bonding is if we consider a hybridization of the orbitals from the original atomic carbon, now not to 4 equal orbitals, but notice we had 3 orbitals spread out in one plane on each atom, right? So we need 3 equal orbitals plus something else for that second bond. And so what it does is it hybridizes with one S and 2 of the P's, sp2, to make 3 equal hybrid orbitals. And then one of the p orbitals is left as a p orbital in the perpendicular direction. So here's a picture of what that carbon would look like in that kind of orientation. So here's the p orbital in this direction. The rest of the 3 bonds that are 120 degrees apart each comprise one hybrid sp2 orbital. Does that make sense? And why would I want to do that? Well, if we're bonding between 2 carbons, we think about one bond as a sigma bond end-to-end overlap of the orbitals from each atom. How does the other bonding occur? It has to not be in the same place, so it's got to be the p orbital on each one overlapping on a side-to-side fashion. So this is what the structure of ethylene looks like. In this hybridization, sp2 hybridization, this is what ethene looks like. Notice it's a flat molecule. If you look on the side, it just happens that there's an S. Okay, it happens that there are hybrid orbitals on each of these atoms, but there's also p orbital left on each one. Okay, and the electron in each of those, they're now being shared in a side-to-side overlapping fashion. Because the p orbital is above and below the plane, that's why we draw it this way. So this is a double bond. The red-blue indicates one bond. And then there's a sigma bond in between that represents the second bond. Okay. This bond we refer to as a pi bond. Whenever you have a side-to-side not an end-to-end, a side-to-side overlap of orbitals, like in a p orbital, that we refer to as a pi bond. Okay, and it's made up of a p orbital from one carbon and a p orbital from the other carbon now interacting. That's what gives rise to the double bond in ethene. So in ethene, how many sigma bonds and how many pi bonds are there? I'm sorry? 5 sigma and 1 pi. How many people agree with that? How many people disagree with that? Okay, it is 5 sigma and 1 pi in the whole molecule. So here, that's a sigma, that's a sigma, that's a sigma, that's a sigma, all those single bonds. One of the double bonds is a sigma bond, that's right here, okay, in between the carbons, and then the other double bond is the pi bond, the other part of the double bond. So a double bond, when you have a double bond, it's made up of 1 sigma and 1 pi. Okay? Any questions on that?
Why isn't it just 2 pi bonds?
Why isn't it 2 pi bonds? Well, if you have 2 pi bonds, that means you'd have to have 2 orbitals left as p's. The hybrids would have to be sp hybridized. And how would you get the other p orbital without something in between? That's the question. So I guess that's not a great answer. A better answer is you always form at least 1 sigma bond because that's the strongest bonding. That's the lowest energy bonding. Pi bonds are weaker and higher energy than a sigma bond, and so it will always, if it can form at least 1 sigma bond, it will. To have a double bond with 2 p's, 2 pi's, and no sigma bond, I think would be a higher energy state. Does that help? I hope. Yeah. So you can see the bond angles. A triple bond is very similar as well, except now to get the third bond has to have an additional pi bond. So notice here in acetylene, compare the structure of acetylene to ethylene here. Ethylene, as I said, is a planar molecule with about 120 degrees between the atom angles. Acetylene is a linear molecule, so there's 180 degrees between any of the atom angles. And the structure, if you think about the orbitals, I've just drawn the sigmas as lines, and then p orbitals. So, like a double bond, we have a sigma bond in between from the overlap of 2 hybrid orbitals in the carbon in the middle. And then we have 1 additional bond, a pi bond, in 1 dimension, in 1 axis, and then perpendicular to that here is another pi bond. So total, a triple bond is made up of 1 sigma and 2 pi bonds. Okay. So in acetylene, there are 3 sigma bonds and 2 pi bonds. There's a CH sigma bond, another CH sigma bond, and a CC sigma bond. Yes, question?
Which orbitals are sharing side to side?
So in the pi bonds, well, this p orbital here, let me just clean this up a little bit. So you'll notice I colored this yellow and blue to try to indicate the yellow. All of the yellow is 1 pi bond because the p orbital extends above and below the plane. And then in the perpendicular direction coming out towards you, the blue bond, the blue orbitals are overlapping side to side above and below the plane in this direction. Okay? Now, what is the hybridization of the carbons? If we've left 2, on each carbon, we have 2 p orbitals left. So the hybrid had to be made up of what? We start with an S and 3 p's. Two of the P's remain as P's, so you're left with what? One S and one P. So that is sp hybridization. Same idea. Here's the atomic structure for carbon. When it hybridizes to be able to form a triple bond, we need to have two p orbitals left on the carbon. S and P is left. Those mix to form two equal orbitals. One between the carbon-carbon overlapping and one to the carbon-hydrogen on each of those carbons. Okay? That explains again the linear structure that we see for anything that is sp hybridized or with a triple bond. Okay. I want to then throw a little curveball at you. Tell me what the hybridization of carbon dioxide is. Well, tell me what the hybridization of the oxygen atoms and what is the hybridization of the carbon atoms. The oxygen should be pretty easy, right? Remember, oxygen has two lone pairs. This atom has one sigma bond, one pi bond, okay, and two lone pairs. So the sigma bond is from a hybrid orbital. We talked about the structure of oxygen, of water, and of ammonia. Where do we put those lone pairs? In what kind of orbitals? Hybrid or atomic? What was the structure of water? Tetrahedral, right? sp3 hybridized. So the lone pairs have to be in a hybrid orbital. That's something else to remember. Lone pairs of electrons are often in hybrid orbitals. So we have a sigma bond, which is a hybrid orbital, two lone pairs, which are in hybrid orbitals, and one pi bond, which has to be from a p. So oxygen has to be sp2. Three hybrid orbitals made up of one s and two p's that have been mixed. And then what's left is one p orbital to form the double bond. So the oxygen has a double bond. The other oxygen on the other side is exactly the same. How about the carbon? That's correct. The carbon has sp hybridization. Why? Why? It's not so obvious because the triple bond is sp. Well, in order to form two double bonds, you have to have two p orbitals. Let me draw the structure of that carbon for you. Do I have the space to do it? Okay, so let's just take the carbon. And I'll draw the single bond to oxygen on this side. That's the sigma bond to oxygen on this side. Those are the two sigma bonds. How do we describe the double bonding to each? Well, I said a double bond has to be a pi bond, side-to-side overlap of p orbitals, right? So if you think about a p orbital on the carbon and a p orbital on the oxygen, that side-to-side overlap would look like that. Okay? If I were to form a triple bond, I'd have to have another p orbital coming out towards you and going back into the screen, right? And overlapping with another p orbital here. Well, it's exactly the same thing except we're forming a bond here. It has to be, the other p orbital has to be perpendicular. So actually this is also a linear molecule. The carbon is sp hybridized because it has two p orbitals left. It just happens that the two pi bonds are just separate atoms, not the same atom, like a triple bond would be. But the structure of that carbon atom is the same as in acetylene carbon. It's linear and has two p orbitals on it. Okay. All right. that's hybridization in a nutshell. If you really think about it, you can some easy ways to remember just looking at the line structure. If it's all single bonds, these are sp3 hybridized. There are no p orbitals left unhybridized. If you have one pi bond and 3 sigma bonds, it's got to be one p orbital left, sp2 hybridization. And if it's 2 pi bonds, whether that's to a same atom in a triple bond or to separate atoms here, it has to be sp hybridization. Yes, question?
It's a little unclear. So if something's in a hybrid, if electron's in a hybrid orbital, does that mean it's in a different orbital entirely, or that it's flitting between two orbitals? What exactly does it mean?
Not sure exactly what you're asking. When we have electrons in a bond or in a lone pair, it's got to be in some kind of orbital. To adopt the lowest energy state, things will hybridize to be able to be as far apart as possible. The only way to get multiple bonds between atoms is to have a side-to-side overlap in addition to the end-to-end. So the end-to-end can still use hybridized orbitals, but that second bond and third bond has to be unhybridized orbitals. Does that help clarify it?
I think I get what it means.
Okay. Ultimately, it comes down to the orbitals describe the shape of the molecule and the shape of those atoms within that molecule. And so that's really helps us to explain a lot of the three-dimensional structures of these molecules. Now let's talk a little bit more about covalent bonds. We've seen a number of different covalent bonds, and if you have a covalent bond between two atoms that are exactly the same, like hydrogen, for example, H2 or F2, those atoms being identical means that the electrons between them, the nucleus is pulling on, attracting those electrons in equal amount. So the electron distribution in that covalent bond, where those electrons spend most of their time within that probability function of where they are at, will be equally shared. That means the molecule, H2 molecule, is not polar. It's completely unpolar or nonpolar. But as we know, not every atom is the same, has the same electronegativity, or they all have different numbers of protons and in the nucleus. They would attract electrons more or less than each other, and there are trends on the periodic table with regard to how much that influence is attracting those electrons towards the nucleus. This is what we refer to as electronegativity. And we have there's an electronegativity scale, the Pauling scale, which every atom's electronegativity has been measured and known. But it is the ability of an element to attract electrons towards itself when it's bonded with another element. That's what we refer to as electronegativity. As it pulls electrons towards it, then you get more of the negative charge closer to that atom. So a molecule can become polarized. Not completely, but partially charged on one end than the other. So electronegative elements attract those electrons. We often use the term electropositive to refer to when we're talking about a bond where one atom is less attracting of electrons, the other one is more attracting of electrons, is the more electronegative. Okay, so there's some of the terms. Here's some examples of atoms in their electronegativity scale on the Pauling scale. For example, hydrogen has an electronegativity of 2.1 on this Pauling scale. Compare that with, say, carbon. Electronegativity of carbon is 2.5. It's not much difference, right? 2.1 and 2.5. So how polarized would you expect a carbon-hydrogen bond to be? Not very much. Not very polarized. Yes, carbon is a tiny bit more electronegative than hydrogen. But compare, say, carbon or hydrogen to fluorine. The electronegativity of fluorine on the Pauling scale is 4.0. That's a significant difference in electronegativity. And if you recall, from general chemistry, there are trends on the periodic table. So as you go to the right on the periodic table, as you go to the right on the periodic table and up on the periodic table, you become more electronegative. So fluorine actually is one of the most electronegative elements. As you go left, it gets least electronegative, and the least electronegative element here actually is francium down in the bottom left. Okay, so those are general trends. The absolute difference depends a lot on how many protons in the nucleus, and the size of the atom. The size of the atom matters too, because if you think about the valence shell, if it's closer to the nucleus, it's going to be more tightly held, and the nucleus will be felt more closely. If your atom is larger and your valence shell is further away from the nucleus, the electropositive attraction from the nucleus is less. So that's why when we go down the periodic table, atoms get larger and larger, the electronegativity gets less because you're further away from the nucleus. Okay, so all of these examples, chlorine, Cl2, oxygen, hydrogen, these are bonds between atoms of the same electronegativity. These are nonpolar bonds. The electrons in the covalent bond are equally distributed between them. And we refer to those as nonpolar bonds. Where we see chemistry happening and reactivity is when we start to get polarization. And that's why it's important to understand this concept of polar covalent bonds. The extreme of a polar covalent bond, if you get further and further difference in electronegativity, then you actually have electrons transfer and you form ionic bonds. Sodium chloride, for example. A big difference in electronegativity is on opposite sides of the periodic table. The charge has fully moved over, electron has fully moved over from one atom to the other, and now we have ionic bonds. But this really is a spectrum, an infinite spectrum of polarization from completely nonpolar to completely ionic. So there is no dividing line that says this is an ionic bond, this is a covalent. Sometimes there are some gray areas there. These examples show some of the polarity, some of the notation we use when we talk about polar bonds. This refers to this sort of arrow with a little plus here on one end, a line on one end. That indicates the direction of electron density. So the arrow is pointing towards the more electronegative atom. More of the electrons are on the side of the more electronegative atom, and so you have a partially positive end of the molecule and a partially plus end of the molecule. Okay? The amount of polarization we measure as a dipole moment, a direction and a charge difference. Notice water, H2O here, the oxygen is more electronegative than the hydrogens. And so the electron density in those covalent bonds are attracted more towards the oxygen. And since water is a bent molecule, it actually has a net dipole in one direction towards the oxygen. Okay. CO2 being linear, it's more negative out on the ends and more positive in the middle. As a linear structure. We can represent this using electrostatic potential maps, and you might have seen some of these kinds of pictures before. But notice these are not full-blown. There's a -1 charge here and a +1 charge there. There's just partial charges, so some greater electron density or some less electron density. Again, it really is a spectrum, a sliding scale of densities of electrons. Here are some electrostatic maps that indicate here. This happens to be HF. These electrostatic maps usually use colors to indicate blue as a positive end, red as a negative end, and then the size of that indicates sort of the amount of charge. So you can see in HF, it's larger and red colored around the fluorine, because that's the more electronegative atom, attracting more of the electron density towards it. And this attraction, this shifting of the electrons within a covalent bond, this is what we refer to as an inductive effect. Inductive effect is the effect of an electronegative atom shifting the electron density in a covalent bond towards it. Okay. Inductive effect. We do have a sort of general rule of thumb. So if you just think again about this, this is a sliding scale from completely nonpolar on the left, where the electronegativity of the atoms there's no difference, to completely ionic on the right. You can have a bonding situation between two atoms that lies anywhere within here. But in general, using that Pauling electronegativity scale that's been measured for all the atoms, if the difference in the electronegativity is greater than 2 on that Pauling scale, those generally then would be considered as ionic bonds. Okay, general rule of thumb. If it's less than 2, it's a covalent bond or sharing of electrons, but certainly can be polarized. So we can have polar covalent bonds, which give rise to how molecules might interact with each other based on polarities, how the reactivity might happen. And one of the key things in organic chemistry is predicting how molecules react. So if you have, for example, a carbon-chlorine bond, let's just think about a carbon-chlorine bond here. I'll draw it here. Chloromethane, for example, is an hydrogens. What, if you think about electronegativity and polarity in this molecule, what's the most electronegative atom here? The chlorine. That's right. Chlorine is the most electronegative. It's pulling the electron density in the sigma bond towards it. Okay? So it means this end of the molecule is going to be partially negative charged, and the carbon is going to be partially positive charged, right? So if this chloromethane encounters another reacting species, let's just say hydroxide ion, for example. Where do you think the hydroxide ion is going to interact with the chloromethane molecule? At the carbon, yes. This is an OH minus. It's certainly not going to put minus towards minus. If you're going to do a reaction, this minus charge is going to be attracted towards that carbon. That's how we predict reactivity patterns and how things happen. And so those are the concepts that these concepts about structure relate to reactivity and help us explain and be able to predict chemical reactions. So that's why it's really important to have these concepts. Okay, so before I move on to talk about acids and bases, any questions about polar bonds, electronegativity, thinking about electrons? I think one thing to think about is that electrons and where they go really predict everything in chemistry. Everything is about bonding and structure, which happens to be sharing of electrons. So if you know where electrons are on a molecule, or electron density, and you know where it wants to be in the end after a reaction, then you can predict pretty much everything. So I think it really is that basic concept of electronics and electronic structure, and that's really important. And that's why I spent a lot of time discussing the orbitals and the shapes of orbitals and how those orbitals look and the positions. Okay, well, let's talk about some reactions. We know that one of the most common reactions is reactions between acids and bases. So we should maybe define these a little bit. So in general chemistry, how did you define an acid and a base? What is an acid? Anybody? A proton donator, something that donates a proton. Yes, that's one definition of an acid. There are more definitions of acid. And it's useful to know the subtle differences between how we describe acids and bases, because there is some relationship between them. An acid, under the Arrhenius definition, that's a very specific definition of an acid. It's a substance that ionizes in water to give protons, in a very specific case. So A is a generic symbol for an anion or some anionic counterion attached to a hydrogen or proton. If it gives up its proton in water specifically, Arrhenius said that's an acid. Okay, and a base is a substance that ionizes in water to form hydroxide ions. That's the Arrhenius definition. But that's a very strict, limiting definition of an acid. I like the other one better, just a proton donor. That's what we refer to as, anybody know the name associated with that definition? Or names? Probably have those in the slide. That's what we refer to as Bronsted acid. Bronsted-Lowry definition of acid. Well, we know that not all acids have the same strength. Some acids are stronger, some acids are weaker. And this is kind of defined by to what extent an acid might ionize or give up that proton in water, for example, or in something else. This is described by the equilibrium ratio, which you can define as the equilibrium constant for the acid, or Ka. And the equilibrium constant is the products over the reactants in an equation, right? The concentration of products over the concentration of reactants. That's the definition of an equilibrium constant. So for an acid, that would be the acid starting reactant is HA. The products are ions, without something else there. Ka is the concentration of hydrogen, proton, A minus over the concentration of HA. I'm not going to have you calculate the equilibrium constant, so worry about that, but I want you to recognize what the Ka means, the acidity constant, and how that relates to how we usually refer to the strength of acids as the pKa. If it's specifically with water, it's the pH we're talking about. The pKa minus log of the acidity constant. Okay, so remember your log functions. Minus log of Ka. So if this describes the equilibrium in a conceptual way, if the Ka number is higher, which side does that equilibrium lie on? To the right. That means we have more of the products than the reactants. So if the Ka goes up, that means the acid must have been stronger and the equilibrium lies more to the weaker side, the products. Right? Make sense? Okay, what about pKa? The minus log of that. If the Ka goes up, you can become a stronger acid. What happens to the pKa number? It gets smaller. Minus log of the Ka, as the Ka increases, pKa number decreases. So just in general terms, the lower the pKa, the stronger the acid. The Bronsted-Lowry definition. A substance that donates a proton is an acid. And a substance that accepts a proton is called a base. Okay, so in the Bronsted-Lowry definition, every every acid must be reacting with a base. It just doesn't ionize to form discrete ions that aren't associated with anything. So for example, if you take an acid, it's got to react with something. Typically, if you do this in water, the proton can be transferred from the A to H2O. And that will form ionic species, but it's not just an H plus floating around. It's actually an H3O plus because the water accepted that. Okay, so some other definitions that you will undoubtedly encounter here. When we define an acid and a base on the left side of the equation, here HA is the acid, H2O is the base. The proton transferred to one of the lone pairs on the water. On the right side of the equation, the thing that gave up the proton and became negatively charged, that's what we now refer to as the conjugate base. Because to go backwards, that would have to accept the proton, right? And the thing that had accepted the proton, now that becomes positively charged, in this case, H3O plus, hydronium ion, that's what we refer to as the conjugate acid. Again, think about on the left side of the reaction, what gives up the proton is the acid. And if you're going from right to left, what gives up the proton would be the conjugate acid. What accepts the proton is the conjugate base if you're going backwards. That's the definition of acid, base, conjugate base. Basically, how you draw the reaction, what's on the left are the acid base, what's on the right are the conjugates. Okay? And the only difference here is when we calculate the equilibrium constant, it's not H plus, it's just H3O plus. Hydronium ion concentration. Okay, so Brunson-Lauer base is acid base is a little bit broader definition than the Arrhenius. It's not just hydroxide. It's what gives up a proton and what accepts a proton. Okay, but even that's somewhat of a very specific definition. Okay, there are other kinds of bases as well. When we think about how reactions might take place, think about this. Here we have NH2 minus and H2O. How might these react together? What would you predict would happen here? Well, a base has to have a lone pair to accept a proton, and an acid has to have a proton to give up. NH2 minus has both. H2O has both. In the previous example, I showed water reacting as a base because it took the proton, right? Well, it depends on what it reacts with. A water can also act as an acid. In this case, I'll share with you the pKa numbers in a moment. In this case, we have something that's already negatively charged. Pretty sure that's going to want to act as a base, okay, because it wants to become neutral. So you can transfer, you can take that one of those pairs of electrons and take the hydrogen off, giving those electrons to the water, and the product is then NH3 plus OH minus. Okay. That's an acid-base reaction. Why wouldn't I have given up a hydrogen from the nitrogen and made H3O plus? What's the other byproduct of that? If I take a hydrogen from NH2 minus and give it to the water, from H3O plus and NH2 minus, that would be probably really high energy to make a double minus charge. That's why I would do it this way. So anyway, if you think about this, this is now an acid-base reaction in equilibrium from the left side of the reaction to the right side of the reaction. How could you tell the position of that equilibrium? Well, if you know the pKa's of the acid and the conjugate acid here, you would be able to predict which side this reaction lies on. Because reaction equilibrium will always lie on the side of the more stable species, right? The weaker species. So this here is the acid, okay? This is the base. On the right side of the equation, which I've written down below, what's the conjugate acid? And what's the conjugate base? Yep, the conjugate base is this, OH minus. What had taken the proton originally is the conjugate acid. Okay, so if we just look at the acid strengths, the pKa's of the acid on each side of the equation, the pK of water is about 16, roughly, 15.7 to be exact. The pKa of ammonia is 36. Which is the stronger acid? H2O, right? Remember, pKa, the lower the number, the stronger the acid. Water is by far the stronger acid than ammonia. And by the way, these pKa units are logarithmic, so it's power of 10 each one change in pKa unit. So this is what, 10 to the 20 difference in acidity. Water is 10 to the 20 times more acidic than ammonia. So obviously the reaction would lie on the side of the weaker species, more stable. It'd lie on the side of the right. Okay? Much more stable, much weaker acid than water. So the more reactive species are on the left, least reactive on the right. This is how we can use some of these concepts to help predict reactions. Okay. I just want to share a few pKa numbers for you to get some idea about what the differences are in acid strength. So if we look at some things that we consider strong acids, HCl. Yeah, you can even have pKa numbers that go in negative. HCl, hydrochloric acid, 3.9, minus 3.9 pKa. Compare that with hydronium itself. And acetic acid, here, acetic acid and water. Okay, so notice the difference in pKa from HCl to water. HCl minus 3.9, it's more acidic, right? Much more acidic than water. Water is about 16. So if you put HCl into water, what kind of reaction would take place? Would HCl take a proton from H2O or vice versa? Right. Water is, in this case, if you mix HCl and water, the water would act as the base and take the proton from the more acidic HCl. Okay, so there's some scale. Here's some more pKa's for some various molecules. I'll put water up there again for reference at 16. Notice organic molecules with an OH group. They're very similar to water. They behave in a similar way. They still have an OH. The oxygen could give up or accept a proton on its lone pair. And the pKa's are pretty similar. 16 versus 17, not a lot different. Notice ammonia, very, very, very weak acid. As a matter of fact, 36 is so high it's very difficult to give up that proton. And organic molecules that are hydrocarbons, methane, pK of 60. Which means you'll never be able to deprotonate or take the proton off of carbon with any known base that we have without something else to do that. Which means, how do you make a carbanion? That's a good question that may come up later in the semester. Some of the things, let's see, how much time do we have? I think I'm going to stop here today. I don't want to get too far into this. We'll continue to talk a little bit more about acidity on Tuesday. We will also start chapter 2 on Tuesday. So please take a look, try to work through some of that homework and let me know how it's going. All right, have a great weekend and a great holiday.